Okay, we're live. Whether the tech is going to work or not, we're going to try it. And we are going to go to lesson 2.2. And we're going to do the square root of a function. You're going, hey, didn't we just do the square root of a function? Isn't that what that hours of homework I did was all about, was square rooting functions? Yeah, but we're going to think about it differently now. In this lesson, I'll even write this in, I'll write a few things in words here. In this lesson, square root is the translation. I'm not going to start with a parent function of square root of x. My parent function for the first example here is y equals x plus 2. If you graph y equals x plus 2, you should remember from way back in grade 8 how to graph straight lines, right? The 2 is, of course, the y-intercept. Oops, get off of highlighter. The 2 is the y-intercept. It has a slope of 1. And then, of course, draw yourself a line. And then the transformation is, what do I change about that black line if it gets put underneath a square root sign? Well, think about it as f of x is x plus 2, so y is the square root of f of x. In other words, square root all the y values on my original graph. So the square root of 0 is still 0. Ooh, there's a word for that. We've seen it already this year. What do you call points that don't change when you do transformations to them? Begins with an I. That's my invariant point. There's another invariant point too, because there is another number besides 0 that when you square root it, it's still itself. And that's why this point here is also in the same place. I guess I should be doing this in red. So this point and this point are invariant. I'll even write that down. Y equals 0 and y equals 1 are invariant. And then I guess the next number that's easy to do is, hey, find out where y is 4. Oh yeah, up here. That's where y is 4. I know what the square root of 4 is. 2. So this red line is the square root of f of x. And notice that's the same graph I'd have got if I did it the way I did lesson 2.1. And don't write this part down, where I start with the parent function here, and then I shift it 2 units to the right. Sorry, to the left. Ugh. So we're actually just doing kind of the same thing. We're just approaching it slightly differently. The transformation this time is the square rooting. So now we got some notes. Note, the radical itself has no values when the original graph is negative. So obviously you can't square root negatives. There are invariant points when y is 0 and y is 1. Oh, I made you write that down. I didn't realize it was in the notes. Sorry. The values of y of the radical function are larger than the original function when you are between 0 and 1. I'm going to just quickly point out that to make sure that makes sense to you, right? Try square rooting a quarter. What do you get? You get a half, right? Give me another fraction that is a perfect square. Try square rooting 9/16. Yeah, but it's not in the chat, so it's all good. I'm looking at the chat. It's all good. Thanks. What's the square root of 9/16? 9/16 is actually just a little bit more than a half, right? But you get 3/4, which is a lot more than a half, right? This is only 1/16 more than a half. This is a quarter more than a half. When you square root a fraction, as it says in the work here, where that value of the fraction is between 0 and 1, you get an answer that is larger than the original number that you square rooted. Every other number in the universe you square root ends up getting smaller, right? When you square root a fraction bigger than 1, Square root anything bigger than 1, you get smaller, right? When I square rooted 4 a minute ago, I got 2. But what does that mean for the graph? It means you get, I'm trying to spell, that's supposed to be a U. Let me try that again. It means you get the very technical term I'm going to call the bulge. Here's the bulge right here. For that space between 0 and 1 in the y direction, the square root is bigger than the original graph. So it kind of bulges past it. That's an important point that we will look at on some future examples here. All right, let's fill out this little chart. What's the x-intercept on my original graph? Well, it's -2. What's my y-intercept when x is 0? Y is 2. What's my domain? It's linear. X can be anything. Now let's look at the square root. Notice the x-intercept doesn't change. How come? Because the x-intercept happens when y is 0, and the square root of 0 is still 0. But the y-intercept becomes square root of 2. And the domain shifts to x has to be greater than or equal to. Notice the x-intercept becomes the place where the domain starts, which makes sense because you can't square root negatives. And the invariant points are, we pointed them out just as y values, but let's actually write them as points. There we go. Oops, sorry. Look back at the graph and you'll see that that's the 2 points right there. Steps to sketching. Cross out the part of the graph where the y values are negative. You can't square root negative, so that part won't exist when you square root it. Place a point on the graph where y is 0, because that's going to be invariant. We'll call that our starting point. Place another point in the graph where y equals 1, because that's also invariant. To find other points in the graph, keep the x values the same and take the square root of the y values. Connect all points in a smooth curve that resembles half of a sideways parabola. And note, in between the invariant points, the square root graph should be above the original graph. In other words, that's the bulge part. I have a question. Yes, thank you. I wrote that backwards. The y value is 0, not the x value. Good eye. Can you guys fix that? My bad. It's right on my page and I wrote it down backwards. Thanks for noticing that. Okay. There's the steps. Okay, now they kind of do this one for me. Actually, they do the next couple for me. But let's pretend like we had to do it ourselves. So I start with the graph y equals x squared minus 1. Oh, back in grade 11, you graphed enough parabolas to gag a goat. So you know that the vertex happens at -1, 0. And you know it's a normal parabola, so it goes over 1, up 1. And it does that in both directions. And then it goes over 2 and up 4. Well, that's because I'm probably drawing in black pen. There we go, see? There we go, sorry. No, I'm drawing in black pen. So I was covering the dots so well. Look at that. I didn't even go to kindergarten. I was coloring in the lines perfectly there. Okay, I'll make the dots bigger. So there. The vertex of the parabola is at 0, -1. And then I know this point, and I know this point. And then I'm going to start. Actually, I didn't really want this point. Go away. If I was drawing this parabola, the next point I would draw would be 2 over and 4 up. So 1, 2, 3. So it'd be like up here. It'd be like up here. But they didn't even get to those points. Good enough. Parabola. Parabola. And I was boasting about my coloring and the line skills, and karma nailed me. There we go. So now, what's the square root of that black line? Let's follow the steps they gave us. I know it's already on the picture, but play along like we can't see it. Step 1, zeros for y are still zeros. So the x-intercepts don't change. There. and there. What's the next thing that doesn't change when you square root it? When y is 1. There and there. What happens between 0 and 1? It gets a bit bigger than the original graph. What happens after 1? It gets smaller. There we go. And then I do the same thing on this side. Okay, let's fill in the actual information they want us to do on it. What's the domain of this thing? Well, the original graph is, and that's the easiest half mark you'd ever get from me on a test. What's the domain of a linear or the domain of a parabola? Well, it's everything. But what is it now when I do the square root of it? Well, it would be x is, okay, I should probably write this better. Save some space. X is less than or equal to -1, and x is greater than or equal to 1. So that's kind of writing it in set notation. If you'd rather see that in interval notation, you have to write it this way. You'd have to say, I go from -infinity up to -1, hard stop. Then you use this funky symbol that means together with, or and. It basically means and. And I go from 1 to infinity. And remember, you have to curve the bracket at infinity, because you can't actually reach infinity. Infinity is not a number you can walk up to in the number line and say, there, I'm at infinity now. Okay? So that's what it looks like in interval notation. Now, what are the invariant points? Well, there's 4 of them on this graph. There is, let's make sure we put the points in the right order this time. There's -1, 0. There is 1, 0. What are the other 2 invariant points? What are these guys up here? Excellent. Yes, that's what they are. They're actually about 1.414 if you want to go decimals, but let's put them as exact numbers. They are plus or minus √2, 1. So there's my invariant points. Any questions on how I figured that out? How did he know right away that it was √2? Because, oh yeah, this point here is basically the square root of the number that was up there at 2. Or, you know, another way I could get it is I could do some algebra. I could say, well, I know that y, I don't really want to spend, I don't want to put that there. It's going to get in the way of my next question. Hang on. Come on. Eraser, come back. Okay. How about I just go back to here and say, okay, how about algebraically? I know that y equals the square root of x squared minus 1 has invariant points when y is 1. So basically I can solve that as a piece of algebra. I square both sides, giving me 1 equals x squared minus 1. I add 1 to both sides, and then I solve for x. And there we go. So that's how I got this number and that number algebraically. All right. Do all parabolas look like those red arms going off, one to the left, one to the right? No, it depends on the parabola. Look at the next one. Follow the steps again. So first of all, what does the graph of y equals 4 minus x squared look like? Well, it looks like this. It has a vertex at 0, 4, and it's a negative in front of x squared, which means it's a downward parabola. If you wanted to find its x-intercepts, they are 2 and -2. You could find that by factoring or just set y to 0 and solve for x. And then, of course, you draw it. Parabola. Oh, trace, hold steady. Oh, there we go, the skilled, steady hands of a surgeon. There we go. Now, what are my steps again? Step 1, I want to do the square root. That point doesn't change and that point doesn't change because those are y zeros. Y equals 1 doesn't change, so those 2 points. It bulges a little between those 2 points. So that's why there's a little bit, I should maybe erase that. There's actually a little bit of air between the black line and the red line. You can see that. Don't exaggerate it. Every once in a while I get a student who goes, "Wow, we want to make sure I can see they know there's a bulge there." Well, would it go backwards? No, it obviously would. You can't square a number and have it go further left. It's not going to do that. So don't do that. Don't exaggerate that. It just is a little bit of air between the black line and the red line on both sides. And then, how did we get this point, you think? It's just a square root of 4, right? So I know it's a curve, so I just curve, oh, there, I'm off again. I curve. There we go. People go, well, it's just a wider parabola. It's actually not a parabola. It's its own curve. I don't think it has a name. But it is a curve. Kind of like a mushroom. A little bit wider at the bottom than it is at the top. There. From now on, it's a mushroom. So, domain of the original graph, y equals x 4 minus x squared, is, of course, again, it's a parabola. So, again, easiest half mark I'm ever going to give you. But what's the domain of the mushroom? Does it go forever in two directions like the first parabola did in example A? No, this is a bounded domain. It begins and ends. It goes from, well, you have to be bigger than or equal to -2 and smaller than or equal to 2. If you like interval notation better, you write it like that. And my invariant points this time? Well, my invariant points definitely are the x-intercepts, which are -2, 0 and 2, 0. And if I want to find those two red invariant points, well, again, I can set the equation y equals 4 minus x squared under a square root equal to 1. And then square both sides. Move the 4 to the other side. Divide both sides by -1. And that's what they are. They are x is minus root 3, comma 1, and x is positive root 3, comma 1. And yeah, I prefer the exact answer rather than a decimal. Because we're not going to let you have your calculator when we do assessment on these. So it's not like you can reach for your calculator and punch in the square root of 3. Anybody happen to know the square root of 3? I think it's 1.7. Oh, I should know the next decimal, but I don't. 1.72? Okay, I give up. I can't remember. By the way, the point is invariant. So notice I put it into this equation, which now that I think about it wasn't very clever of me, because it's an invariant point. I should get the same point if I plug it into that equation. And then I have one less step. I didn't have to worry about squaring both sides. Oh well. Live and learn. Here's our third parabola shape. What if you have a parabola that doesn't touch the x-axis at all? Well, as you can see, it kind of turns into a smile. So how do we get it? Well, first of all, let's graph this original parabola here. I was trying to underline that, not cross it out. It's a parabola with a vertex at 1 to the right and 3 up. There it is. Is that drawing big enough for you so you could see I was drawing? And then a parabola always goes, when the number here is 1, a parabola always goes 1 to the right and 1 up, 1 to the left and 1 up, and that's enough to know the curve. So I draw the curve. Parabola drawing. Oops. There we go. Parabola drawing, parabola drawing, parabola drawing, parabola drawing. So there, pretend like I had to draw that parabola myself. Now, where does the red one come from? It's those same steps. Step 1. Where's the invariant points? When y is 0. There aren't any. Next, invariant points when y is 1. I don't have any of those either. Next, just square root everybody. What's the square root of 3? Again, I don't know, about 1.7. What's the square root of 4? Ah, that one I can find. 2. What's the square root of 4? 2. Make a curve. It's wider than the original curve was, which makes sense. It's not going up as fast because the numbers are getting square rooted. And that's it. That's all there is. So I think we'll call that one a smile. Let's finish off the notes. The domain, again, No shock here. X is an element of reals. What about here? Yeah, also X is an element of reals, right? This thing should go on forever. But what are my invariant points? None. So there's the three things that can happen when you try to square root a quadratic. You can get the two wavy arms, you can get the mushroom, or you can get the smile. Those are technical terms. I just square rooted all the y values. So the question is, I don't get how you got this red one in C. And again, let me go and point to the points again. How much is y here? It's 3. What's the square root of 3? I don't know, about 1.7? There you go. How much is y here? That's a good point to pick because 4 is an easy number to square root. 2. How'd I get this point? It's there. And then I know it's a curve, so I just drew a line through it that was a curve. I also know that it's symmetrical on the same axis of symmetry that the original parabola had. Remember that word? Axis of symmetry from grade 11? Is that bringing back memories? Okay, a couple more. Example 2. If I give you a graph, how do you do the square root? You just follow the steps. Step 1, I'll do this in black. Step 1, that is an invariant point. Step 2, oh, this is just like your quiz yesterday that I did. I told you this, right? I made the answer key wrong twice. On the third answer key, I noticed what I was doing wrong. Look at the graph. Where's the invariant point? Am I on the invariant point right now?
No.
How come? Because it's not counting by ones. There's a special place in the depth of my heart of hatred for graphs that don't count by ones because they always fool me because I'm not very observant sometimes. So the invariant point is down here at 1. And then, okay, how about this? Square root of 4 is 2. There we go. I think that's enough. I know what shape it is. Again, it's a sideways parabola. It bulges a little there, and then it goes off like this. And actually, I could maybe go all the way to 9 and square root that to get to 3, but I don't know. I don't know where that is. Good enough. Something like that. All right. What about this guy? What kind of a parabola square rooting is this one? Is it the two arms, the mushroom, or the smile? It's the two arms. How come? Because it has two x-intercepts. So invariant point, invariant point, invariant point, invariant point. Let's make our lives easier. I know the square root when y is 4 jumps down to 2. 4 jumps down to 2. There we go. Don't forget the little bit of a bulge. Don't exaggerate it. I just want a little bit of space. Just a little bit of space between those two lines. Thank you very much. Everybody get how I did that? All right. Your turn. You get to make one. Okay. All right, so did you give me a y-intercept there? Oops, come on, pen. Did you give me a y-intercept there? Or sorry, x-intercept, I mean, with a y value of 0 here. That's going to be an invariant point because y is 1. And we never quite make it to 4. Looks like it'd be around here someplace. And that would give me a point at 2. So this one's kind of long and flat, but it's still a curve, right? It's still a sideways parabola. Something like that. Okay. So first things first on the next page, it wants us to do a little bit of grade 11 algebra. Find the x-intercepts of y equals x squared minus 25. Okay, that shouldn't be hard. X-intercepts happen when y is 0. And then you have two choices in your algebra selection this evening. You can just move the 25 to the other side and then square root both sides. Or, remember that x squared minus 25 is what you call a difference of squares? Waiter, I think I'll have the difference of squares this evening. Plus 5 minus 5. So that means that I have x equals negative 5 and x equals 5 are my two x-intercepts. Okay? Let's do the other one, number 2. Set that to 0. Move the 3 to the other side. This is not a difference of squares, so I can't factor it that way. So I'm going to move the 3 to the other side. And then what happens? Yeah. You can't square root a negative in real numbers. So this thing has no x-intercepts. In grade 11, if you'd have said it has no solutions, we'd have said, good for you. You have equated x-intercepts with solutions of equations. And we'd have given you a sticker like you were in elementary school. Good for you, grade 11er. In grade 12, I'm going to try to dissuade you from using the word solution now, because I'm kind of not being honest if I said that x squared equals negative 3 has no solutions. It has perfectly good solutions if I don't care that I'm not in real numbers anymore. And next year, when you guys move into just about any course beyond grade 12, you do lots of math without being in real numbers. They're called complex numbers. You can square root negatives in complex numbers. So you could say no real solutions and still get your sticker, but don't say no solutions anymore, because that's not really true. Okay? So anyway, no x-intercepts is for sure true, because the square root of negative 3 doesn't exist in real numbers. Let's jump down to number 3. How do I solve that one? Well, let's see. I would solve this one by, again, setting that to 0. And I think I would divide both sides of this equation by negative 2. 0 divided by negative 2 is still 0. And then, whoops, and then whoops. And then I have x squared minus 16. I'm going to use my difference of squares again. So x is equal to plus or minus 4. And then what about number 4? Okay, well, let's see. Set that to 0. Divide both sides of the equation by 5. Okay, now you can do this as a difference of squares if you want to. You just have to think of it as, come on, pen. Some people don't like thinking about it that way. And if you don't like thinking about it this way, if you're like, that's cheating, it's not a difference of squares if they're not actual perfect squares, then I'll say, okay, fine. We could have, at this same step, just done this. And actually, you could do this for all of them. I don't really care which way you do your algebra. Again, you're a grown-up grade 12 now. I shouldn't have to tell you how to do algebra. Feel free to just move the 10 to the other side by subtraction, and then square root both sides, and you get the same two answers. Doesn't matter to me which way you think about it. Okay? All right, and now the next instructions say sketch the graphs of 1 and 2. On the same graph, sketch the square root of each graph above. So for 1 and 2, what does x squared minus 25 look like? Well, I'd have to go all the way down here. This 5, 10, 15, 20, 25, so I'm actually counting by 25s. And then I go up, and then this would be, well, I guess this would be 5, 10, so that'd be 10, so that means I have a 5. So it'd be this, Be a very skinny parabola on the scale that I'm working on. And then what would that look like when I do the square root? So this is, let's label it. Is it y? Yeah. So this is y equals x squared minus 25. Now let's do its square root. I'll do that in blue. It has an invariant point there. Come on, blue. Where are you? There we go. It has a variant point in there. There's an invariant point there, an invariant point there. Then there'd be another one at 1, but it'd be really close on this scale, so it's probably just going to look like that. I'd have a hard time seeing the actual bulge in there. All right, what's the next one? Y equals x squared plus 3. Oh, that's going to be this guy. 1, 2, 3, and then x squared, just your average everyday. Oops, oh my God, that's way off. Your average everyday parabola. But what kind of shape is this going to be when I square root it? It's going to be the smiley face, because the square root of 3 doesn't quite make it to 2, and then it's going to do that. Because all the y values get square rooted, and since they're all bigger than 1, they're all just going to get to be smaller numbers than the ones above them. And so now explain why it is important to determine the x-intercepts. Well, whether or not you have x-intercepts determines what kind of graph it is. Okay, oh boy, we're out of time. You can try the practice ones on the next page, page 13 yourself, and we can go over them, actually 13 and 14, and we can go over them tomorrow. And then we're going to do, actually before you guys leave the room, sorry, we're going to do this practice ACC tomorrow, so I'm going to hand it to you guys so that you can have it at home tomorrow. So my apologies for going right to the buzzer there. There you go. There you go. So this is what we're going to start class with tomorrow. Just to make sure we've got 2.1 solid, and then we'll finish off 2.2. We might even get started on 2.3. 2.3 doesn't have a whole lot of graphing to it. It's mostly algebra. You're probably going, finally some algebra. All this graphing. Sorry, but this course is a lot of graphing. Okay, thanks guys. Enjoy the rest of your day, and we'll see you online tomorrow and in person on Monday. All right. So I'm going to stop my video.